right, let's see what we can do here. Rotational variables, angular acceleration, blah, 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 blah. It'll be fine. This is going to be great. You know what's great about circles? They don't go anywhere, at least right now. Right now, we've got these circles, and they're like pinned in the middle, and they just rotate. And I just want you to appreciate how amazing that is. Because like later, you're going to be in classes where they're like, this is rotating, and then it's going this way, and then it's going to, and you're going to be like, oh my gosh, please make it stop. But right now, look at this beautiful circle. Well, okay, shush. It could be a beautiful circle in the eyes of its mother. There. Nah, that's saying better. Anyway, there's a circle, and it's rotating, and it's awesome, and it's just sitting in the middle, and it's not moving, and you guys don't know how amazing this is. Okay, so this very, very important concept right here being demonstrated. Forget that angular velocity word for a second. Basically, if you have a circle, this is critical. If you have a circle, I'm trying to get over here. Okay, circle. Okay, you may be aware that the radius, get that, and if you go all the way around, the circumference is 2 pi r, right? And that's why we define 360 degrees as 2 pi radians. You're like, actually, I didn't know that, but thanks. And that's what you're here for, is the fun and mystery of science and math and engineering. I don't really know why you're here. Maybe you're just bored and lonely and love learning about angular velocity for no reason, or maybe somebody's making you watch this video. In any case, okay, this is important because if, say, I only went through a portion of it, okay, and if I measure that portion in radians, then I would only do that percent of the circumference, right? Maybe, like, if the 100% of the circumference is 2 pi, then pi, or theta over 2 pi would be the percentage of the whole circumference. And what that means is the arc length here is given by the percentage of the circumference. And you're like, okay, I get that. Like if I go through half of the 2 pi, then I get half the circumference. If I go through a quarter of the circle, I go through a quarter of the circumference. Okay, so theta over 2 pi equals 2, or times 2 pi r. Look at burps. And it turns out that we have theta r. If you measure theta in radians, then this s over here that I wrote, this is called the arc length. So the arc length of a circle is the radius times the distance, or the arc subtended, I think maybe they say, of that little thingy, the theta. Basically, it's theta r, and I forgot it, and I could never remember it for years, and then someone showed me where it came from, because I thought it was just a random equation someone made up, and of course it isn't, because that's the amazing thing about math and science and physics. Well, really math and physics. I don't know about biology, because I could be stranded on a desert island for 4,000 years and never know that that's called a flat-topped canary or something. But what's amazing about math and physics is, like, no matter what, you would eventually come up with this if you were, you know, had nothing else to do. Okay, so all that said, if I am looking at the arc length, now, there are a couple of things that I can do. If I take the derivative of this, just very, very gently, a very gentle derivative with maybe a couple of asterisks, the derivative of position is velocity, right? And then I would have d theta dt times r plus theta times dr dt. Okay, maybe. Now, I think this whole section is uniform circular motion, maybe, or at least we'll call it fixed axis rotation. Yeah, so for the moment, we're going to go with r doesn't change with respect to time, that the radius is constant. And so what we end up with is that the velocity is d theta dt, okay? And we have a special word for d theta dt, so we have d theta dt times r. Well, we call d theta dt omega. R, I meant to say r. So omega, being the change in the angle, is called angular velocity. So basically everything that you've done so far has been like lefty, righty, and uppy, downy. And then this last chapter 10 and 11, not the last, but the chapter 10 and 11 here, we're going to look at roundy roundies. So not uppy, downy, lefty, righty, but just roundy roundies. So as we're going roundy roundies, omega is angular velocity. Now, how shall I say? It can be a little weird in that, let's see, how do I want to say this? Okay, so does it make sense when I say that all the velocity, if I have a circle here, all the velocity is in the tangential direction at any given point? Does that make sense? Tangential. Like the velocity is always tangent to the curve, because that's how you make a curve. And I feel like we've talked about this before. But the velocity is always tangent to the curve. So you can put a t here, but it's kind of considered extra, because it's just assumed that you clearly, the velocity is the tangent to the curve. So it's defined as omega times r. So if I'm just going to be in, what do you call this, magnitudes, if I ddt it again, ddt, I get the acceleration in the tangential direction would be d omega dt times r plus omega dr dt. And again, I'm going to assume that dr dt is 0. And what's really cool is, by really cool, I mean, I don't know what I really mean by that, but we can define alpha. Okay, this is an alpha, just so you know with my handwriting. This is an alpha is d omega dt. And if omega is angular velocity, then d omega dt should be angular acceleration. I knew you had it. Okay, angular acceleration. So the tangential acceleration is alpha r. Okay, so if I have a point going around in a circle, the tangential acceleration is alpha r. So that's the, like, if I say I'm going around in a circle and I'm pushing on the gas pedal and I say my speed is increasing, like if I say my speed is increasing, I don't know, what's fast? 60 miles per hour squared. I have no idea anything about cars. Is that fast? That's probably 0 to 60 miles an hour in 1 hour is probably not impressive. But, you know, this is not a very good car. To be fair, my car doesn't work right now, but that's okay. Okay, so that tangential acceleration is the acceleration that you, as the driver of the car, are like, that's my acceleration. Because from my own perspective, in my tangential direction, that's the way I'm going. Now, remember, we know what this one is. This one is v squared over r, because we found that out like a whole long time ago. Now, the good thing is, what's kind of cool, is we can actually rewrite this. So we know v squared over r, so the acceleration in the normal direction, so normal like toward the radial, v squared over r, and we know that v squared can be written as omega r. So we have omega squared r squared over r, so we have omega squared r. So you can basically, let me see, you can write that as v squared over r, or you can write it as omega squared r. They're both equivalent. So it's just the same ta-ta, same ho-ho, same, everything's the exact same thing. It's amazing. And this is the tangential. And so I labeled this one is the tangential acceleration, and this one is the normal acceleration. That's the acceleration at the center. That's the acceleration that, like, your car is not specifically, you're not pushing on the gas and making it go to the center. The friction on your tires is keeping you from flying out, and you're kind of, you know, steering toward the center. But really, whenever you're saying, I'm pushing on the gas, so this is my speed, it's increasing by this thing, that's your tangential acceleration. Your normal acceleration is basically the vector version of how do I keep myself going in a circle. And it's kind of a weird concept, and we're toward like the second half of the semester, and people get tired and their brains are like, this is dumb. And so here's all of this that they're just talking about. And now they're talking about, okay, right hand rule. Okay, so now take your left hand. It's the one that if you look at it, it makes an L. Left hand. Okay, now sit on that. So I'm going to sit on my left hand. So I can't use my left hand. You're only allowed to use your right hand. Now, so the idea, and this is kind of strange, the idea is that whenever you're rotating around something, which way does that vector point? And you're like, well, the vector is pointing around. And it's like, well, vectors can't point around. They have to point in a straight direction. So take your right hand, put it on your piece of paper, and then your thumb should point out of the page. Okay? So thumb points out. Okay? That is the direction of the omega vector. So if we have, and this is also stupid, not stupid, it's for right-handed people. And I'm right-handed, which is really weird because both my parents are left-handed. But if you're going counterclockwise, just physically because our right hands are shaped the way that they are, we have decided that the way our fingers curl is counterclockwise, right? Because if this is my hand, these are my fingers. See, I have fingers, finger, finger, and then I have a thumb. And my thumb is pointing out of the page. That means that the omega vector is pointing out of the page. Okay? This is so important. Oh my gosh, so important. Thumb's pointing out of the page, fingers are going around. Now, cross products. I know we talked about cross products a while ago. Well, not if you didn't watch all the videos, but if you did, we talked about cross products a while ago. And we talked about cross products that was like A cross B equals C. And with the directions, it's like your fingers go in this direction and you curl around the B direction and your thumb points in the C direction. Okay, so this is important because what they're about to tell you is that V is omega cross R. Okay, so it's going to be great. You're going to love this. V equals omega cross R. Okay, so put your hand on your piece of paper. Remember, you're sitting on your left hand. So your fingers come out of the paper because this is omega cross R. Actually, I'll put the V on the other side. So omega cross R equals V. And you're like, I thought you just said V equals omega R. Well, that's true if everything's flat. Okay, so this is for flatsies. And everything's great. So for flatsies, we're good. And flatsies and perpendicular e's, then that's correct. Otherwise, it's not. So we really do prefer to define this as a cross product, and you're a big, giant calc-based physics person, so you can handle this, I swear. Okay, so now back to this omega. So your fingers are this dude. So your fingers point out of the page. And then I want you to pretend that this is R. Okay, so now curl your fingers toward R. And now look which way your thumb is going. So if my fingers are pointing out of the page, finger, 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 and I curl them, I don't really know how to draw it all, down like this, I look like a velociraptor, then my thumb points this way. That's the direction of the velocity vector. Okay, this is so crazy, but it's super awesome and it's super powerful, which basically means that from now on, anytime you have R's and omegas and V's, you don't have to worry about them all being like perpendicular or perfect. You just have vectors and you play vectors and you do vectors. You never have to think about it again. It's amazing. So again, fingers out of the page, curl toward the R, like in the direction of the R vector, and then your thumb goes in the direction of the V vector. Okay, I don't really know how much we're going to get into that in this, but it's something you should physically see because you're going to need it eventually. So whenever I say the velocity is the omega times R, so if I go omega times R, and if you think about that coming out of the page, right? So, and if you want to think about it with cross products, like omega cross R is omega R sine theta, So if they are already, so if omega is coming out of the page, like that, then they are at 90 degrees, so it's omega r sine 90, and then that's omega r times 1, so that's just omega r. So if, like on 2D, we're generally okay because everything is already, like if omega is just coming flat out of the page, we're good, and if r is just flat on the page, we're good. But you need to understand that things can get more funner, I guess. So you have omega r, and then the magnitude of that is v, or whatever. But what's cool about the cross product is, so right now, this v, it doesn't tell you what direction it points. If you use the cross product, that gives you the magnitude and the direction. So omega r by itself just gives you the magnitude, and it only works if omega and r are perpendicular to each other. If you use omega cross r, you get this beautiful perpendicular vector. It's super awesome. And if you want to know about it, what's he does it's meow. This one up here, meow, meow. This is actually, and I don't think your book's going to get into this, but the normal acceleration vector is omega cross r. So like if your fingers come, you do the inside of the parentheses first, so your fingers come, let's do fingers out of the page. 1, 2, 3, 4. Fingers out of the page, cross toward R, and that's omega cross R goes this way, right? Omega cross R goes that way, because that's where your thumb goes, and now you omega cross that. Okay, so now you've got a second circle, omega still coming out of the page, so this guy goes to this direction. And omega still coming out of the page, so you've got your fingers coming out of the page. Hold on, I've got to adjust a little bit. You've got your fingers coming out of the page. 1, 2, 3, 4. You curl them in the direction of the thingy we just did. Chomp, 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 chomp. I don't know how many fingers I have. Chomp, chomp. Hold on. Oh, yeah. Omega cross R. Omega cross R. Omega cross R is that way. Omega cross R. Oh, and then your thumb is going, yep, that's right. Your thumb is going this way, which is actually in the negative R direction. So this is to the center of the circle. To center of circle. And you're like, no, but it's pointing to the edge of the circle. Yeah, but it's a vector, right? So the vector is pointing this way. So basically from here to here. You're like, but you put it here. Well, that's because I'm messing around. I'm just trying to, your thumb, your hand, it's about the directions. It's less about the position. Technically, you can move forces along their line of action, but that's for another day. But anyway, so what I'm saying is cross products are amazing and you need to get into them because all the cool kids like cross products. And I think that is, oh, see, look, there you go. It's totally doing stuff. We'll come back to this in a bit. Sorry. I got so excited about alpha cross or omega cross R. I forgot to show you alpha cross R. But alpha cross R is just the same thing. So if I know I'm accelerating this direction, then my fingers come, and then I've got a radial direction this way. So my fingers come, I forgot what color my fingers are, come out of the page, and I curl toward, my fingers go this way, and then my thumb goes this way. And you might say, well, wait a second, what if I'm actually decelerating? Okay, so if you're decelerating, then you're going into the page, right? So that means your fingers go, how do I draw fingers going into the page? Probably as well as I draw them coming out the page. Fingers going into the page, and then I have to turn my hand like kind of backwards to curl them up and up. No, I think I upped them the wrong way. Up. And then my thumb is pointing this way. So that's the direction of my angular acceleration. So, or if your velocity, angular velocity is considered negative, that means it's into the page and you're going clockwise. So I guess let's just make sure we write that down. So if alpha or omega are negative, then that's considered clockwise rotation. And then if they're positive counterclockwise, and the only thing you can just do is look at your hand. And I'm sorry that people make clocks stupid. I don't know who to complain to about that, but you know, do your best. But hopefully that's basically where all this comes from, is so that the magnitude of, although the magnitude of the tangential acceleration is alpha r, the magnitude and direction is alpha cross r. Do make sure you don't flip the directions, because if you remember anything about cross products, A cross B is not equal to B cross A. In fact, A cross B is equal to the opposite of B cross A. So if you get them in the wrong order, you'll get the negative of the answer that you actually want. So just something to keep track of going forward. Okay, so this is either the video where you go, oh my gosh, science is amazing and everything is mathematically consistent, or you go, yeah, duh, I could have figured that out on my own. So we'll see what happens. Okay, so we know that angular acceleration is d omega dt. Now, a long, long time ago, like weeks ago at this point, we had a similar equation, a equals dv dt. And we made an assumption where we said, let's pretend acceleration is constant, because a lot of times, like, gravity is constant. So we're going to do the same thing. Let's assume angular acceleration is constant. Okay, so we have alpha dt equals d omega. Integrate, integrate. We're going to start time equals 0 to time equal t from some unknown starting velocity, angular velocity of final velocity. And since angular acceleration is constant, it can come out of here. And on the left, we end up with a, or alpha, t minus 0, and omega 2 minus omega 1, also known as omega 2. Did I do that right? Yeah, my brain is not working. Omega 2 equals alpha t plus omega 1. And maybe, if your brain is still functioning, which it, to be fair, may not be, and that's okay. Who needs a brain? We're just doing physics. Meowp, 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 0t, meowp, v1, v2, and see how we got this a t minus 0. Whoa, whoa, dude, check it out. This is amazing. Or not, but it could be really cool. Look, it's basically the same thing, but in roundy rounds. So this is lefty righties and uppy downies, and this is roundy rounds, and it's basically the same equation. It's so fantastic. I love science and math so much. Okay, we're going to do the same thing again, where we do that omega, come here girl, omega is equal to d theta dt. Okay, that was a weird dt. Okay, but I know alpha t plus omega 1, like some initial omega. I think your book likes omega naught. So omega 1 equals omega naught, in case that bothers you. I'm just making it the initial one. dt equals d theta, and we're going to integrate from theta 1, or I guess theta naught, to theta, and then from 0 to t. And on the left, are you just going to be like so shocked when we get 1/2 alpha t squared plus omega naught t. And on the right, theta minus theta naught. And then whenever we fix it, we get theta equals 1/2 alpha t squared plus omega naught t plus theta naught. And the crowd goes wild. Maybe. I'd like to hope so, because it's this thing, right? Yay! Look, it all is mathematically consistent. And you know what else we can do? We can take the alpha equals d omega dt and put it over omega equals d theta dt. And from there we can get alpha over omega equals d omega dt divided by d theta dt. And then the dt's cancel out, and we end up with alpha over omega equals d omega d theta, also known as alpha d theta equals omega d omega. And if alpha is constant, and we integrate Then we have alpha theta minus theta naught equals 1/2 omega squared evaluated here to here. And we've got, if I put the 2 over here and I do some fun math, I get omega squared equals omega naught squared plus 2 alpha delta theta, which is literally just this thing. And you're like, ugh, I thought I was away from that, and no, you're not, because it's amazing, and science is fantastic. So I don't know how you could ever just not be deeply satisfied on a fundamental level with how this works. Okay. Anything else that we super duper need to go over? I think the biggest things that you need to be worried about in stuff like this is, making sure you know what the, circumference of a circle is. And then whenever they talk about revolutions per second or something like that, just remember a revolution is a full circumference. So a revolution is 2 pi radians per second. Now, radians isn't officially a unit. It's considered a unitless measurement. So I could say it's 2 pi per second is the rotationiness. But sometimes if you're given something in revolutions, you're going to need to convert it to radians. Or if you're given something in theta, like in degrees, you need to convert everything to radians. So we are now officially in, for the purposes of rotation, everything gets converted to radians territory. Okay, so let's just look at this one. So fisherman hooks a big fish, good for him, that swims away, pulling the line. So much drama. The whole system is initially at rest. The fishing line unwinds from the wheel a radius of 4.5 centimeters from its axis of rotation. Oh, like in the picture. I was trying to figure out what they were talking about. The reel is given an angular acceleration of 110 rads per second squared for 2 seconds. What is the final angular velocity? Well, hot potato. So I know that the final angular acceleration is given by alpha t plus omega naught, because that's just like final velocity equals at plus b naught. It's the same thing. So 110 radians per second squared times 2 seconds plus it's initially at rest. So isn't that just 220? Why am I? Okay, yeah. Okay, I'm not going crazy. How many revolutions does it make? Okay, so this is maybe more interesting. So it goes 1/2 alpha t squared plus omega naught t plus initial theta, but it's originally at rest, and let's just say the initial theta is 0. So the theta that it goes through is 1/2 110 t squared. So we have 110 t squared divided by 2. I guess I probably could have done that in my head. Is 220 again. Thank you for giving us the same number twice. That's really, really nice. 220. So this is 220 radians, and it asks for how many revolutions. And you know that 1 revolution is 2 pi radians. So there's other ways to do it, but I like to learn one way and, never learn anything else in my life. That's been always my big goal. So I just treat it like a unit conversion. So I'm going to cancel out the radians, and I end up with revolutions on the top. So 220 over 2 times, and what I do is I forget to put the 2 pi in parentheses, and then I get the answer wrong. Thank you. Why did I put a period there? No reason. I'll put a period here. Okay. All right, so 35.0. So theta is 35.0 revolutions. So it runs 35 times around. Kind of makes sense? Okay. And then, these are all the same kinds of problems. It's just like instead of going lefty-righty and uppy-downy, you're going roundy-roundy. And I think if you just make that connection, these problems are relatively straightforward, but just making sure that you remember how to do this conversion and don't get in your own way. As long as acceleration is constant, you can use these beautiful, wonderful, perfectly lovely equations that we came up with over here. So as long as everything is constant. As long as angular acceleration is constant, we can use this one, we can use this one, and we can use this one. That's pretty fabulous.